Hello everyone. In this session, I'm going to talk about one of the articles prescribed as a part of current issues for FRM Part 2 exam for 2018. So this topic is all about machine learning. Is it really a revolution in risk management? Is it going to change the face of risk management and compliance? So it was an article that was published in one of the journals, and we are going to talk about some of the important aspects of that article. So here the main elements that I would be discussing from that article. Let me tell you again, this entire presentation is based on the content that has been written as a part of that specific article. So I'm going to talk about the process of machine learning. So what do we actually mean by machine learning? What are the different types of machine learnings? What are the different approaches to machine learning? So that would be the first part. Then I'm going to look at, coming to the financial services sector, what are the various applications of machine learning? What is being used currently in the financial services sector, and in which areas machine learning has been successful, what are the limitations of machine learning within the financial services sector, and a few such kind of aspects. Then we move on to specific aspects like coming to credit risk and revenue modeling. What are the different kinds of techniques relating to machine learning that have been used? Similarly, when it comes to handling fraud, what has been the experience of the financial services industry with respect to machine learning techniques? And similarly, with respect to surveillance of conduct, market abuse like rogue trading, insider trading, how has what was the real success of machine learning in these specific aspects? And what are the different kinds of techniques of machine learning that can really improve the entire surveillance aspect? So these are the various things that we are going to take up as a part of this session. So coming to the process of machine learning, when I say what is machine learning, so remember there are two important words, machine and a learning. So means there is a machine. Here when we are saying machine, it's a computer or a system, right? So it is learning. Just like you learn, I learn, we have different styles of learning. So the machines also typically learn. How do they learn? They learn through the data that we are supplying to them. So the input that we give to the machine, it tries to understand it, it tries to comprehend it, and it tries to do some kind of a generalization. Just like I've given you a book and I've asked you to learn. You have your own way of reading through the book. So that book is the input. The same book is given to many people. So the input is the same. But the way you comprehend it will be different from the way I comprehend it. So those kind of different ways in which the learning happens are typically called as the algorithms. So all of us understand things in different ways. All of us make some kind of generalizations. So that generalization is being done by a computer as well. And after that, once we have learned something, we'll use that knowledge for some kind of applications. Now the same thing can be done by a computer as well. It will use the knowledge that is generated through this data for some kind of applications. So that is what is machine learning. So basically the system is going to have the analytical power based on the input that we are giving to it. So because of that reason, in the financial services sector, we are going to expect machine learning to really improvise the operations and the performance in the financial services sector. Now, is it something new? Did this concept not exist earlier? Or what is the key driver to this entire process of machine learning? We have been seeing that the IT is changing, the information technology is changing quite rapidly. Lots and lots of innovations, lots of ways of handling huge data, storage capacities. So the IT world has been experiencing lots and lots of innovations, and even the data. Coming to the data, in the financial services sector, if I look at the volume of transactions that happen on a day-to-day basis, it is huge. Now, that is the kind of a data that is available in the financial services sector. So the data is huge. The computing innovations came up. And how do I link the various data elements that are being captured? I want to really look at the fluctuation in the price, right? Just for an example, I want to look at the fluctuation in the price of a particular stock with various economic related factors, various company related factors, various competition related factors. So I can model so much of complex relationships between the variables. So probably when I have to do that kind of a high-end work, manually things are not possible. Now that is the reason I want machines to do that kind of a job for me. So the need for modeling lots of complex and non-linear relationships between the variables to understand the typical structure of the various variables, machine learning is going to be the solution. If I have to look at overall broad category of machine learning, there are two major types of learning. Even in our case, we talk about those two, supervised and unsupervised. When I say supervised, I have a goal. Whereas unsupervised, I don't have any goal. It's just like I have to prepare for an exam. I have to get through the exam. So my preparation, my learning would be more and more targeted towards a goal. So that is a supervised learning. Whereas in unsupervised learning, I'm just given a book. I have to understand the various patterns in the book, the various elements of the book. So there is really no goal. The goal may be created at a later point. Right now, it's only the learning that is being done. So just like that, even in our case, we do the learning in two different forms, the supervised and unsupervised. Supervised means there is a goal. So typically, I would be using supervised learning for a kind of prediction purpose. So I would be linking my dependent variable or a prediction variable. I want to predict something. So typically I call it as a prediction variable or a dependent variable. So in this case, it's the stock price I want to predict. and I want to learn about the stock price. So what is the supervised learning here? I want to learn about the stock price in relationship to all these variables. So there is an objective. I should be able to understand stock price with respect to all these variables, right? So that is what is the supervised learning. I am trying to comprehend these two as a relationship, right? So that is what happens in a supervised learning. I'm trying to build a statistical model wherein I'm trying to build a relationship between a prediction variable and the predictor or the explanatory variables or the inputs. So I want the machine to typically learn from the data. So these two try to learn whatever is the way you want to build the relationship between these two. I want the system to use different algorithms and then learn so that tomorrow when the competition changes, the economy changes, the company's factors changes, I should be able to come out with a prediction of the stock price. So that is what goes as a part of supervised machine learning. Now, there is some difference between this way of supervised machine learning and a typical statistical model like regression models. Right? In regression also we talk about similar kind of a relationship. But the only difference is when I talk about, let's say, a linear regression model, it assumes that the relationship between the price and those input variables is primarily linear. They are normally distributed. So it makes some kind of assumptions regarding the distribution of the variables. Whereas in reality, the data may or may not be linearly distributed or may not be normally distributed. So another advantage of machine learning is it really makes no assumptions regarding the relationship between the dependent and the independent variables. So when there is no relationship, no distribution, that is assumed, in that case we call them as non-parametric analysis. So machine learning can be done using the non-parametric analysis models rather than assuming some kind of a distribution about the data. So that is what supervised machine learning can do for us. And coming to unsupervised learning, as I have already said, there is no goal or objective for learning. I'm just given a book. So I'm just given, the system is simply given a set of data. Now, there is no estimation, there is no relationship building. So how does the system learn? It tries to understand some kind of patterns in the data, some kind of structures in the data, and tries to segregate the data based on all these learnings. Right? Probably the one of the major applications is clustering. It creates different clusters of the data which we can use at a later point for different business purposes. So the unsupervised learning, there is no objective, only the data is given, which means there is no dependent variable at all. So it's only the input data that is being given. Study the input data, identify the patterns from the input data, and if possible, segregate the various data points and create different clusters. So that's what we do as a part of unsupervised learning. All right. Now, let's look at the various approaches to machine learning. Approaches are nothing but different methods different techniques, right? How do you learn? Now I have to make my machine learn. So there are different techniques for it, or there are different algorithms that are going to address that learning problem. So different methods are available. Now, first of all, I need to know what is my problem. What do I want to do? Do I want to do some kind of estimation, right? Or do I want to identify some kind of patterns in the data? So I have different kinds of business problems. So different business problems give rise to different techniques. There may be hundreds of techniques for one kind of a problem, because it's as good as saying I can learn things in 100 different ways. If I give the same book to 100 people, I'm sure 100 people are going to read it, learn it, assimilate it, and generalize it in 100 different ways. The same thing goes even here as well. I'm making the system to learn, but I have different techniques to make the system learn. When I come to supervised machine learning, where there is a dependent variable, right? Supervised machine learning, there is something to build a relationship between a dependent variable and various input variables. Typically, I see there are two categories of models. One, I want to predict a categorical variable. Categories, right? A person default or not default, yes or no. I want to predict this kind of outcomes. So my dependent variable is a kind of a categorical variable, or in very simplified terms, a binary variable. So if my objective is to predict this kind of a number, this kind of a variable, then I have a different approach. In some cases, the variable that I want to predict is a quantitative variable or a numerical kind of a variable. In that case, my approach is different, right? Broadly, I can look at, though there are various other dimensions as well. Broadly, I look at the supervised machine learning as either the prediction of a categorical kind of a variable or the prediction of a quantitative or a numerical variable. So, any prediction of a numerical variable typically is called as regression. Any prediction of a categorical variable is typically called as a classification problem. So supervised machine learning has addresses two major kinds of problems. One, prediction of a quantitative variable, or prediction of a categorical variable. Again, let me tell you, this is at a very high level. Within regression, there are hundreds of methods, and within classification also the same thing exists. So regression, we are talking about prediction of a continuous dependent variable, or a quantitative or a numerical kind of a dependent variable. Now, within this, as I said, there are hundreds of methods. So depending on how I am building a relationship, what kind of relationship is being built between the dependent variable and the set of input variables, the methods differ. So the learning can be done in a linear manner, which means a linear relationship is built between the dependent variable and the input variables, or it could be in a non-linear method. When it comes to linear, typically we have different approaches like partial least squares regression, principal component analysis based regression. So there are different kinds of regression methods. These methods typically assume a linear or build a linear relationship between the dependent variable and a set of input variables. Whereas there are so many penalized regression approaches, which means the more complex the model I'm trying to build, there is a kind of a penalty that is being applied. So it's a kind of predictability that is coming up versus complexity, right? A simple model which can do a good prediction is a much better model compared to a complex model which hardly enhances any which hardly is a value add above the simple model. So the more the complexity the model is becoming, there is a kind of a penalty that is applied. So that is what goes into the penalized regression approach. So we have the lasso regression, we have elastic nets. So I'm not going into the calculation aspects or the technical aspects associated with each of these approaches, but here my intention is to tell you at a broad level there is a regression kind of technique to predict a quantitative variable, and this particular regression can assume or can build linear relationships between the dependent and the input variables or nonlinear relationships as well. Similarly, when it comes to finding or predicting a categorical variable, we put them as a classification problem. So my dependent variable is a discrete variable or a categorical variable, and if there are only two categories, we even call it as a binary kind of a variable. So there are again so many techniques to do this. Decision trees is one major technique. Now again, let me tell you, within the decision tree itself, I can talk about 20 different kinds of decision trees. So that's how the algorithms techniques typically grow. But the broad category decision tree, it is looking at the various yes no kind of questions. So there is a tree kind of thing that is being built typically, right? Wherein the different input variables that you are giving, based on those input variables, the categorization into a yes or a no, default or a no default, is typically being built. So a tree of this sort is built with the various input variables that are being provided. So this is how a decision tree works. And similarly, when I look at a support vector machine, so there is a kind of a plane. So let's say we are talking about the various points, various input points, right? I plot the different input points, and let's say the output also. Output, because it's a supervised learning, there is an output or a goal as well. So let's say these are all S's for something, and these are all no's. Okay, so the support vector machine typically draws a line or a plane like this and tries to divide the data in such a way that a large number of y's are separated on one side and large number of n's are separated toward the other side. It might be very well possible that there could be a couple of n's here, a couple of y's here, but to whatever extent possible, it tries to segregate the distance between the y and n's by drawing a kind of a line or a plane or some such kind of a stuff. So there is a kind of a margin that is being applied between the two classes, and this margin is the most optimized. When I say why am I saying optimized? Because there could be 10 lines that could be drawn which can segregate between the two classes. The best possible line. That is the reason we are using the word optimized. So it looks at the observations. It tries to draw a line or a margin across the observations in such a way that the two classes or multiple classes that are there, They are simply separated more and more efficiently. So the approach to learning is different. Now if you see the decision tree, it tries to understand what is the characteristic. Let's say GDP greater than 7%. The stock price went up by more than 2%. GDP less than 7% and inflation less than 5%, some such kind of combination, the stock price is between something and something. So it is trying to understand or generalize different sets of rules or decisions linking the output to the input. That is what happens in a decision tree. Whereas here it is trying to segregate the different classes, and based on that segregation it is trying to trying to build a line or a plane which is segregating between the values more and more efficiently. Is this fine? Alright. Then we move on to unsupervised machine learning approach, where we are talking about clustering. As we have already discussed, in unsupervised machine learning, there is no target, there is no goal, there is no dependent variable. Only the data is being provided. So the dependent variable is lacking for us. The main thing that happens is the patterns are being understood in the data. The data is grouped into various clusters based on their characteristics. So similar, all the data that are having similarity in the characteristics, they will be put into one group or a cluster. The ones that are having distinct characteristics are segregated from the rest. So that is what happens as a part of the typical clustering problem. Now, we talked about different kinds of approaches to do prediction. Prediction means majorly it's a supervised learning. Either I predict a quantitative variable or a categorical variable. And we said there are different approaches, like different kinds of regressions that are available to do the supervised learning. And apart from that also, you would see at a later point that there are several other techniques like neural networks, even support vector machines can also be used for predicting a dependent variable. So we see that there are different kinds of techniques for predicting dependent variables, whether it is categorical or numerical. Now, which method to use? Whatever is the method, first of all, I need to have an objective, I need to have a clear understanding whether my intention is to do good prediction, or is my intention whether I am intended to talk about good explanatory power. See, basically what I am talking of is, let's say my intention, my problem is predict whether a particular loan applicant, right, as an application I am talking about, I want to design a model to predict whether a loan applicant is going to default or not default. And if the model gives that there are high chances of default, better not give a loan to him at all. So now if my model is predicting that this person is going to default, that there are high chances for this person to default, the next point that comes in is on what basis or what is the reason behind it. So whatever the model has been built, I should be able to explain here. I require explanatory power to the model. It should tell me because his income is very low, there is a high chance of default. So such a kind of thing talks about the explainability of the model. What variables are contributing to the model? What are the important variables? What are the unimportant variables? I've given so many inputs. I've given 20 inputs and built a model for predicting default versus non-default. Now I need to know which ones are significant, which ones are insignificant, right? So that is what we are talking about, the predictive performance. Which variables are contributing more, which variables are not contributing more, means I need an explanatory capacity from the model. There are a few models which are majorly black box. When I'm saying majorly black box, I can get the result, but I cannot explain them that anywhere easily to the target audience. So depends on is my objective. If the system is able to do good prediction, is it sufficient, or does it need to have the potential to explain the reason why it has predicted that way? So that is what is differs between the various models. So explanatory versus predictive. Some models may be extraordinarily good at predicting, but I may not be able to interpret them very easily, whereas in some cases the reverse is very much possible. So a very good predictive model can be complex, but the ease at which I am able to interpret it, explain it, may not be possible at all. And the other important point that needs to be looked at with respect to machine learning is overfitting. The more and more I'm training the data, so it's as good as I give a book, I make you read and read and read and read. What is going to happen? You may mug up the book completely. You may learn the book to such an extent that anything I give, any question I give from that book, you are going to get 100%. But the moment I give you question from some other book, possibly you are going to fail very badly, because the way you have learned is more and more customized to that particular input data only. It's not generalized. You are going to learn deep into the questions that are being given as a part of that book itself. Anything that comes outside, you would not be in a position to do anywhere better. That is what we call as overfitting. The system has learned, generalized in such a way that you try to apply it on the same data, it is 100% successful, but you try to apply the model on a new data, it fails miserably. So that is what is called as an overfitting problem, right? So the relationships don't come up in a very generalized way, they become more and more specific to each record. These kind of things are very prevalent in non-parametric, where you are not assuming any kind of distribution between the variables. Non-linear, so the models, wherever the models are complex models, the learning can happen even to the core, which means the learning becomes too much specific to the data that I am providing rather than a generalized kind of an approach. So when I test that learning on a new data set, it's going to fail very miserably. So these are the different kinds of approaches you see towards machine learning, right? Now I want to move towards how is this machine learning useful when it comes to the financial services sector. Now, the next thing that I want to look at is the application of machine learning within the financial services sector. What are the different applications where we can use this mechanism? I want to streamline different business lines through this: credit, underwriting, compliance, client management, risk management. There are various applications I can think of where these machine learning models can be used. especially when it is with respect to streamlining, automating the lines of business. Today, there is a lot of digital revolution in terms of capturing the data. So, lots and lots of data is being captured at regular intervals of time. The transactions that are happening in the financial services industry is very huge. So there are high frequency set of transactions, and through the digitalization we are able to capture them quite comfortably. Similarly, the consumer data, not just based on the form that has been filled, I get lots and lots of unstructured consumer data. There are a lot of interactions that are happening over the phone with the customer, right? Or sometimes the customer uses Facebook or some kind of social media and tries to post something regarding the product. So there is a lot of unstructured information about the customer that is coming from various sources. So thanks to this digital revolution, we can capture all this kind of a data from the customer as well. Now, analyzing that data, building patterns from the data, and using that data for some kind of a prediction purpose is something that is being enabled through machine learning. If you look at some of the applications again specific to the financial services sector, the new capital regime, there is a lot of reporting requirement. All large exposures need to be reported almost on a daily basis. The liquidity measures need to be reported. So there should be something that should be able to collate the whole data, do the all calculations on almost on a real time kind of a basis, because all these reports have to be generated almost on a regular basis. So the banks have to report large exposures, the liquidity measures, collaterals, capital levels. You could see that the reporting requirements have gone up quite drastically. Means I have to upgrade myself with the digital revolution. The computations, all these things need to happen almost on a real time kind of a basis, right? Similarly, when you look at the CCAR, all the financial institutions, they really need to consider the impact of more than 2000 economic variables. How do I build such kind of models? Definitely, I require the help of the machine learning algorithms. Similarly, the Solvency 2 for insurance companies also has increased the reporting requirement. So with the increase of the reporting requirements, there's a huge amount of data that is coming in, huge amount of processing that is required, huge amount of reports that need to be prepared, and all these things will become more and more feasible, easy to work if machine learning is integrated into the operations, right? So which means if I have to handle that much of huge amount of data, I have to create high number of reports, means my data needs to be well defined. It's not that I capture, make spelling, make capturing errors, and then after that do the cleaning exercise. It can't happen that way, right? The data that I'm capturing needs to be well defined and structured. I need to have an automated way of capturing the data. And once the data is there, there should be different ways in which I can aggregate it, I can summarize it across the group, and even the reports have to go on time. Means my IT systems, the information technology infrastructure needs to be sophisticated enough for doing this kind of an exercise. And apart from very structured kind of a data, we are also talking about low quality data, more and more unstructured. As I've already talked about, the interactions with the customers, the social media interactions, there are so many these kind of data which is not in a simple tabular kind of a format. We call it as unstructured data. Sometimes the phone conversations, sometimes the images, right? Sometimes the handwritings. These are all unstructured kind of a data. So we are capturing large amount of low quality unstructured data from the customer through various apps, digital interactions, social media feeds, payment systems. There are different amounts of high frequency unstructured data that is coming. Based on that, I want to assess the sentiment of the customer towards my product. Today, the customer management using all these machine learning techniques, using all these digitalization kind of techniques is becoming one of the very, very prominent areas, right? Digital marketing, trying to understand the behavior of the customer through various means, not just structured feedback given by the customer, but through various sources. So all this is becoming feasible again as an application of machine learning. So even if I have phenomenally large data sets, machine learning has the capability to cope with them. It is very much comfortable even going to the granularity of the analysis as well. So that's the reason today the financial services sector requires machine learning models, algorithms on a very niche and defined kind of a basis. More sophisticated algorithms are very much required. Now, coming to specific use cases, let's say the credit risk and revenue modeling. There have been quite a few attempts, or there are already instances in the world where small and medium enterprise credit risk has been assessed. A few banks have actually tried neural network kind of an approach to model SME credit risk. There was also an instance where company's solvency, whether a company is the company going to be solvent or a bankrupt, a kind of assessment is being done through support vector machines. We also have instances regarding CART algorithms, classification and regression trees. That is what we call as a CART algorithm. So there were instances where CART algorithms are applied to large data sets for building various consumer credit risk models, especially in the retail loan segment. My data is too huge. So because of that huge data, CART kind of algorithms can be used to really predict whether a particular customer is going to default or not default on a particular type of a loan. Here, the difference is I have traditional credit related factors like the age of the person, the gender, the debt to income ratio, right, or any other debts that the person is already having before taking this particular loan, the income levels of the person, the occupation of the person, some such kind of very general credit factors are considered along with the various banking transactions that are going to happen. This is more and more of unstructured kind of interactions, kind of the social media feeds, etc. I combine all these things, and based on that, I'm going to build a model which is going to improve the predictive power definitely. So that's where the machine learning models are coming into picture. Similarly, for capital requirements, there are lots of linear regression models, logic regression models, probit regression models that are already being used by the companies to determine the capital requirement for performing stress testing and even for various internal management procedures. Right? So we talk about the applications of regression. All these kinds of regressions are in place for various credit risk modeling. We also talk about the different classification tree approach, classification methods like decision trees, support vector machines, especially with respect to probability of default. I want to predict what is the probability of default or what is the loss given default. So these kind of stuff for PD modelings. Also I can use machine learning models. For LGD modeling I can use machine learning model. So the applications are again very wide in the credit risk modeling. But a few important points that we have to consider in this context. Again, the overfitting problem can come up quite heavily, right? The learning can happen so deep to a large extent that any kind of a prediction on the same data, same set of variables is very much feasible. But if the variables change slightly from the input variables, the predictive capacity falls quite drastically. So that is what we said as overfitting, but that can very well be a problem with majority of the machine learning models. We have to be careful in terms of designing the solution so that this overfitting problem can be avoided. So different kinds of non-parametric and non-linear approaches, we have already talked about them: support vector machines, neural networks, deep learnings. We said that they are all black boxes. They are good, they may be good at doing good predictions, but when I want to explain what are the factors contributing to this model, their explainability becomes much weaker. They are majorly practically black boxes. I don't know what is happening in them. I give an input, I get the output. But what is happening inside? Because there is a lot of looping that happens inside. There is a lot of feedback process that goes inside. I don't even know what is majorly happening inside this black box. I get the predictive model, I get the output, given an input, it will be able to predict, but if I have to explain the important factors driving the prediction and all, it would be slightly complex. So because of that reason, if a regulator has to prescribe these kind of models, it would be difficult. Or even if the companies say I'm using a neural network as an internal model for my capital requirement, it may be difficult because I would not be able to explain the regulator as to the way the model is calibrated or computed. All right. So that's one of the limitations that needs to be considered with respect to applying machine learning techniques to the credit risk modeling. The other way you can very well look at is whatever the linear regulatory models that are being prescribed or that you are really submitting using the explainable models, like if I use a linear regression or a logistic regression, the logit or a probit kind of regressions, I can very well explain the way the model in very good clarity. So where I can use the machine learning is initially I decide the parameters through this approach, but I can very well enhance a few parameters using the machine learning method when I submit the things to my supervisor. So the existing parameters can very well be enhanced by using the machine learning approaches. So that's where I can supplement my typical explanatory approaches versus the predictive approaches that I am getting through the machine learning. Similarly, the CART, classification and regression tree kind of models, they can be good at explanation because we talk about, they just give interpretable decision rules. They don't talk about any kind of distribution assumptions or anything. So the decision rules that are being coming out through the CART algorithms are easily interpretable. Logic is very clear, but they model the nonlinear behavior as well. So these kind of probably the card trees are very much feasible in terms of implementation in credit risk and revenue modeling because their explainability is decently good enough. Now, moving on to in what ways machine learning can help in fraud. We have already seen that the credit card payment infrastructure of the banks, they have integrated the monitoring system as well, which means on a real time basis, the moment I look at a transaction, I'm going to say whether this transaction has the potential to be a fraudulent transaction or a clean transaction. And if there is any kind of a suspicion relating to a fraudulent transaction, my card is blocked in a real time. Now, this is also a kind of an application of the machine learning itself because huge amounts of historical transactions, credit card payment related data has been given as an input to the model. The models have learned through various techniques, and based on that, they are trying to give their output regarding the potential fraudulent activity that is going to crop up on a particular card. So, data sets are very huge in case of credit card transactions. So because of that, the training becomes much more easier. The testing becomes robust, right? And validations are very much possible. Historically also I have lots of transactions where I could clearly say that this was a fraudulent transaction, this was not a fraudulent transaction. So the clear bifurcation between fraud and non-fraud with respect to historical data is very clearly available, and because of that reason, especially in terms of identifying credit card frauds, machine learning models have been very successful. But when it comes to money laundering, anti-money laundering or terrorism financing kind of activities, still today I don't have a machine learning algorithms running quite effectively. They are still relying on some kind of rule-based systems. Of course, so these rule-based systems, there is a possibility of a good number of flaws, that is the false positives, right? There might be because then every suspicion is going to get converted into uh, every small suspicion is going to be identified. Many a times it turns out that it's not a money laundering kind of an activity. So, rule based may or may not be that effective. Large number of false positives or failed results are going to crop up. But machine learning still has a potential to get into this activity. But of course, there are quite a good number of constraints in this process. There is no universally agreed definition of what is money laundering. So I cannot segregate a transaction into a money laundering transaction versus anti-money laundering transaction. I don't have too much of bifurcation. Just like in case of credit cards, any transaction I can clearly classify whether it's a fraudulent transaction or a non-fraudulent one. But in case of money laundering, terrorist financing activities, I can't really segregate the transaction into money laundering and anti-money laundering. So this makes the training process very difficult. Use a kind of any kind of a machine learning algorithm and try to train the system. The historical data is not that good enough, so the training methods may not be that appropriate. And even the financial institutions do not receive feedback from various law enforcement agencies with respect to what is money laundering, what is not money laundering, how do I classify a transaction as money laundering or not. So today only a basic suspicious activity is being given as an input, and based on that the machines are getting trained. So the input to the training is not that sophisticated today, and that's the reason the predictive model that comes out, the output that comes out also may not be that robust. And even unsupervised learnings also can be applied when it comes to anti-money laundering, because we are only trying to, we don't have a goal, because we cannot classify the data into money laundering or not. There is a possibility that unsupervised learning methods like clustering can very well be applied. Just observe the various patterns from the data, create clusters. See those elements which are very distinct from the rest. See the patterns of data which are distinct from the rest, and probably there might be a kind of suspicious activity on those particular data items. So the clustering basically works based on identifying the outliers. They are not linked with the other elements. So all the data points are within this cluster, but I see one or two data points way away from this cluster. So these two data points come out as the initial suspicious kind of activity. So anomalies. Based on these anomalies, I can think of probing more into these anomalies to identify whether this transaction is a fraudulent one or not. So sometimes unsupervised machine learning techniques like clustering can very much be helpful in terms of identification of fraudulent transactions. Coming to surveillance of conduct and market abuse, especially with respect to identification of rogue trading, benchmark riggings, insider tradings, various such kind of activities, identifying them at the earliest, machine learning is going to play a very important role. So the companies are developing, the financial institutions are developing various automated systems, trying to understand the behavior of their traders in multiple ways so that these activities can be identified at the earliest. And today where the machine learning is coming into picture is, along with the trading information, the behavioral information of the trader, the email traffic, what kind of emails he or she is sending, the calendar items of the trader, the phone calls, all these things can very well be linked. Try to understand the behavior of the trader, and based on that also there is an early indications of any such kind of market abuse in trading activities can be identified, right? So there is a normal behavior, and any trader's behavior deviating from normal, there is an alert that will be sent to the compliance team. So all this is possible because of the machine learning itself, right? But of course here there is lots and lots of pattern identification. We don't have the historical transaction data talking about this particular transaction was a breach or this was not a breach kind of stuff, because the financial institutions cannot share this information, which is very sensitive to a machine learning developer. So obviously, because they cannot share this information, supervised learning is very much is not at all possible in this. So majorly it's an unsupervised learning kind of mechanisms itself, and majority of these are black box, as we have already seen. Right now a specific kind of a behavioral identification is very much needed. What kind of customers are going to default, or sorry, what kind of traders are going to breach the conduct? I need to identify the behavior, but if I am building a black box model, it only says whether a particular trader is going to breach or not. But it would be much more appropriate for me to take a preventive action in terms of hiring the traders itself when I come to know that this kind of behavior is going to is leading to major insider trading activities. So again, different kinds of machine learning algorithms definitely are going to play a role in surveillance of conduct and market abuse as with respect to trading activities as well. So these are some of the things that I wanted to cover as a part of this session. So we have discussed at length on all these various areas which I shared with you as a part of the initial agenda. I hope you got a fair amount of an idea regarding all these areas which are being picked up from the article for the FRM Part 2 purpose. In case you have any queries regarding the same, you can very well call me on the number that I have provided below, or you can even email at the email address given below. Thanks a lot for listening to this session. Thank you very much.